once we have our table of values from our graphing calculator, we are going to write them down. In this case, because we're just sketching, accuracy, not to worry about it. -3 is 30, -1 is -0.7, 0 is -0.25, -0.7, 30, and 58. Okay, so I have chosen these values because they are around my asymptotes. The way that we found our asymptotes is by factoring the denominator, and I wrote them out in green. These are my asymptotes here. So -5 is way out here on the left, +58, so it's somewhere up high. -3 is closer to the asymptote and is +30, so it's somewhere here. -1 is on the right side of the first asymptote, so -1, 0.7, let's say it's somewhere here. 0, -0.025 is closer to the 0, so it's here. And then 1 is a mirror of it. And then +3 is 30, somewhere here. And +5 is 60. So what this tells me, remember, I cannot cross an asymptote. So approximately, let me just double check that I did this correctly. Approximately, this could look like, I'm just going to double check my my graph here. You can see if you push the graph button, on your graphing calculator, you will see what it looks like. And mine looks a little bit weird. So I'm going to push the zoom button. And I'm going to go scroll down to where it says zoom fit and hit enter. And it will choose a zoom window where you can see it best. Okay. You see where it kind of glitches? That is where my asymptote is. You see how on the left side it kind of goes down and then starts curving up? That means our function is going to look like this. Curves down and then goes up, but never touches the asymptote. In the middle, you can see this is almost like the vertex of a parabola going down like this. Right? And on the right side is a mirror of the left side. So this is going to go down and go up like this. Okay, so finding points close to the asymptote kind of tells us where the piece of the puzzle is. When looking at this particular rational function, we can't really see a whole lot other than we know where the asymptotes are, but graphing calculator will give us a little bit better of a picture. Okay, the key point that I want you to remember when we have rational functions is the non-permissible values in the denominator. If they factor out, and cancel, then we call it a hole in the graph. So this means if I could factor the top and get something like x plus 4, x plus 2, and I have a numerator and denominator that cancel, then I still have a non-permissible value, but it's just a point. It's a hole in the graph. However, if I have a non-permissible value that does not cancel out, then I have an asymptote. Okay, here we had x plus 2, x minus 2. We could not factor the top, so they don't cancel out. So then we have an asymptote at those points. X equals -2 and +2. Those are asymptotes. And I hate spelling this word. So from now on, we're going to call them HAs, where HAs where y equals some kind of a value, and VAs for vertical asymptote where x equals some kind of a value. So these are vertical asymptotes at x equals plus or minus 2 in this case. We will dive into this more deeply as we go through this unit, but this is just a reminder of things that you should have seen at least once in prior classes. All right, algebraic functions can be constructed using any operations, starting with a polynomial. Irrational functions are automatically algebraic functions. Why? Because here's a rational function. The way I created it was by multiplying some stuff, adding and subtracting some stuff, dividing some stuff. So I followed all the algebraic operations, so rational functions are automatically algebraic. And there's lots of different examples of what those are. So when we build a function using these pieces, these are algebraic. If we have a root function that is technically could be algebraic, but it doesn't have these base functions here. Oh, sorry. Exponential ones and root ones are sometimes tricky, but algebraic means we use the BEDMAS stuff, essentially. Okay, trigonometry. You just did this. What is this function of, or what is the graph of a sine function? Let's say that 1 is 1, 2, 3, 4. Call that 1. 1, 2, 3, 4. Call that -1. And let's skip over and call this pi by 2, pi. 3 pi by 2, 2 pi. And the same going backward. Where do we start a sine function? Top, middle, or bottom? Middle. And then it goes up or down? And where does it hit 1? Pi by 2. Up, middle, down, middle. Oops. Put that little dot too low. Okay, and if I go backwards, am I going up or down? Down, middle, up, middle. Okay. When we look at the symmetry of a sine function, is this even or odd? Odd. Because it is like a reflection, but in opposite directions, right? It's symmetric about the origin. Okay, cosine. Where do I start a cosine? At the top. And then I go down or up? Down, so middle, bottom, middle, top. And then going backwards, same thing. Down, middle, and top. Even or odd? Even because they are mirrors of each other about the y-axis. Okay? Tangent. For the tangent function, let's say, same idea. This is going to be pi by 2. This is going to be pi, 2 pi out here. Okay, starting at the origin, what am I doing? Tangent. What does tangent look like? Kind of like a squiggle. If I were to compare it to a power function, which power is it most alike? A cube, yeah. So it kind of looks like this. And it has an asymptote. Where is the asymptote for tangent? Y pi over 2.
That's where we can calculate that value of 10.
Why? Yes, but why is there an asymptote there? No. No. Sorry, say your thing again. You said it, or you said it. Who said it? Cos equals 0. Sorry, my dyslexic brain was waiting for you to say sine equals 0, and then I'm like, no, he's right. What are you doing? Yes, wherever cos equals 0, I have a non-permissible value. This is not something that I can cancel out, so the non-permissible value results in a vertical asymptote. Yes, so wherever cosine is 0, and based on our graph, cosine is 0 at pi by 2. So anywhere where cos is 0, we have a vertical asymptote. So then what happens if I go beyond pi by 2? There's another tangent line, and it's just shifted to the right or shifted to the left. Is it odd or even? Odd. Wonderful. Thank you for correcting me and not just going with whatever I say. Okay, exponential. All right, we can do this. An exponential function is where we have y equals a base that is a number and x is in the exponent. So rather than x being the base and, for example, 2 being in the exponent, our base is a number and our x is the variable in the exponent. So it looks like this. Okay. 2 to the x. Let's plot some key points. What would be true no matter what the base is? What x point could I always graph? No matter what the base is. It could be a 2, a 4, a 5. Which is? Where y is 0? Where is x 0? At 1. Right? So we have an intercept when x equals 0, and it will always be, if I don't have a translation, it'll always be y equals 1. So I can put whatever base in. As long as there's no plus and minuses on the outside of the equation, I don't have to worry about it. I can replace that 2 with any number, as long, and x is 0, intercept will always be 1. So that is a key point that we have to know. What happens if x is a negative number? What happens to my y values? It gets smaller because it's the reciprocal, right? So if I have x less than 1, then I end up with y essentially less than 1. So I end up with very, very small numbers.
They never touch 0 either, so that's like
Why don't they touch 0? I agree with you.
Because there's no power that can make two multiplied up to get us.
Yeah, there is no value that I can put in x to make y equals 0. That means the x-axis is my horizontal asymptote. Y equals 0 is an asymptote. I can never touch it because there's nothing I can do with this equation to make it 0. Okay, so now what happens as x gets large? You have exponential growth. So as x gets greater than 1, we end up with essentially something that's going off into infinity. Comfortable with this? Okay, now let's look at what happens when my base is smaller than 1. Here, my base was greater than 1. I have exponential growth. What happens when it's less than 1? So again, when x is 0, I have an intercept of 0. That's my key point, doesn't change. But now, as my x gets larger, I have decay, meaning it's getting smaller. We call this, maybe I should write this word, decay. When the base of an exponential is less than 1, I'm also going to say between 0 and less than 1. Essentially, I want a small fraction rather than a large fraction, right? And as it gets negative, if x is getting large but in the negative direction, what's happening to my value for y? It's growing. Okay? And I want you to think of, does that make sense? If I have 1 over 2 to the power of negative 3, this is the same as 1 over 1 over 2 to the power 3, which is the same as 2 to the power 3, right? So we have decay, and our asymptote stays the same. We cannot make this 0, so it's not going to cross that line. Comfortable with this? Good. All right, let's take a look at the logarithmic function. Now, a log function is the inverse of a exponential function. So when we're looking at an inverse, do you remember what the visual transformation looks like? Okay, so if I make f, the function, negative, that represents a reflection upside down, yeah? If I make the x value in the function negative, that reflects side to side backwards. If I do the inverse of a function, it is also a reflection, but about what point? The diagonal. Thank you, Michael. All right, so if I have a diagonal and an exponential growth function, this is e to the x growing. What would the log function look like if I reflected it? Yeah, kind of sideways. It's going to, hold on, I need to write my key point in the right spot. E to the x has, okay, what would be my new key point if I'm doing the log function? So I reflect it over, where's my key point? On the x-axis. So this is now my key point for a log function. Maybe I'll do it in black so we don't confuse it. So this is y equals log x, essentially. Okay, now my arrow, if x is getting larger, what is it doing? Bigger or smaller? If x is positive and getting larger, getting bigger. So we're looking at something like this. And then again, as we get closer to 0, it is going like this. Can I have a negative log, negative x in the log? No. So now my asymptote is a vertical one. Vertical asymptote at x equals 0. Okay, and I'm going to erase my exponential function. I just drew it in for you to see how to derive the log function as an inverse. Okay. We have a vertical asymptote at x equals 0, and we have a key point at 0, 1 for when x is 1. Okay. Any questions here? What if x is between, sorry, what if my base, the base of my log is between 0 and 1? So it's a fraction, a small fraction. Log x, the generic one with a base greater than 1, we have the reflection of this graph, the exponential. This is a log of a fraction, so it should still be the reflection of this one. So where's my key point? -1. And what direction am I going? Oh, sorry, I put that in the wrong spot. Negative. Hold on. Here we go. Here is the reflection. Where is my key point? Give me the coordinate. 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 Ah, there we go. 1, 0. Okay, we're going across the diagonal, right? Across the diagonal line. Thank you, thank you. So we are going to 1, 0. Okay, now, if I were to reflect the second quadrant arrow, it's going up and to the left. If I flip it over that green line, where is it going now? It's going to go down, but is it going to go down and to the left or down and to the right? Down and reflect this over this way. Down and to the right. Okay. So like this. Okay. Second half in the first quadrant right now is going down and to the right. If I flip it over that diagonal line, where is it going? Up and to the left. There it is. And we are still going to have a vertical asymptote at x equals 0. Are we remembering this? Oh, right, you guys didn't graph. Okay, we'll do logs, lots of logs together. Don't worry about it. Okay, but this page needs to be your BFF. Okay, I want you to really live, breathe, and memorize this page because you're comfortable with the other ones. You need to be comfortable with this one too. Okay, let us classify these functions. So what we have done so far, we have labeled our catalog of functions. We have linear, it was number 1, polynomials, number 2, square roots, number 3, reciprocals, number 4, rationals, number 5, algebraic, trigonometric, exponential, and logarithms. We have 9 functions. So looking at the equation, what is A? This is an exponential function. What is B? Okay, what do we call a power function? Could be a power function. What's another way we could label it? Look back at your 9 categories. Could be more than one. Yes. Could be quintic. Quintic is part of what category? Polynomial. Okay, what else could it be? Polynomial. Does it have a function that's part of BEDMAS? Yes. So what do we call those? Algebraic. Okay, what about C?
Rational.
Tempting to say rational because I see a fraction.
Radical.
Tempting to say radical, but there is a fraction.
Oh, algebraic.
Algebraic. Rational means there's a fraction with an x in the denominator, but no roots. Algebraic. I don't know how to spell that word, but I'm just going to guess. Okay, radical means there's a radical, but there isn't a fraction with an x in the bottom. So we're categorizing them. Okay, what about D?
Polynomial.
Yep. Could it be anything else?
Power and algebraic.
Yep. Are we comfortable? All right. We have 30 minutes. I want work time. Here is your homework assignment. Get to work.